me very slowly introduce you to Mariana Carrillo Gonzalez. She will be telling us about warped black holes as a double copy from Mini-Twistor space.
Well, thanks to the organizers and the scientific committee for allowing me to give this talk. First of all, I'm going to have to explain to you what is the double copy. I'm assuming not everyone is familiar with it. Then I'll move on to explain what is the Mini-Twistor space of ADS3. And finally, at the end, we'll reach actually how to construct a double copy for these warped black holes. So let's just start very general. We know that gauge theories can look very different from gravity. And we know that gravitational theories can be very complicated to do calculations, like scattering amplitude calculations, because they're highly nonlinear. So instead of a standard description of gravitational theories, we can ask a question if there is a better description, in a sense, that simplifies how we do these calculations. And one of the options is the so-called double copy. So if you go on shell and you want to construct scattering amplitudes, one thing that you can do is to start from the scattering amplitudes now of your Yang-Mills theory. And you're going to expand this as a sum over various graphs. And you can split this in separate things. One is going to be a color factor. So this contains everything that depends on your gauge group. So for example, like structure constants. Another part is going to be the so-called kinematic factor in blue. And this only depends on polarization vectors or your momenta. And then at the bottom in the denominator, we just have all the propagators that will appear in your usual Feynman graphs. So if you split the amplitude like this, there's one thing that was noticed by Bernd Carrasco and Johansen, and was that there's some kind of duality between the color and kinematics. And this duality just refers to the fact that the color, by default, satisfies some algebra, for example, Jacobi relations, and the kinematics for these gauge theories also satisfy the same algebra, meaning that you can exchange these numerators depending on the particles that they involve, and they can satisfy the same algebra that the color factors. So once you have that, you can exchange the color for kinematics and then construct another amplitude. And this is indeed a well-defined amplitude that instead of having now gauge symmetries as the previous one, now is invariant under diffeomorphisms and corresponds actually to the low energy limit of string theory. So it gives you a gravitational theory with not just a graviton, but a dileton and a two-form field. But in principle, you can do certain operations to get rid of this and just obtain Einstein gravity if you want. Furthermore, you can also decide now, well, I don't want the kinematics, I want to remove the kinematic factor, and I want to put a color factor. And now you'll reach this theory that's called a bi-adjoint scalar. It has two adjoint indices, and it has cubic interactions. It's not very physical, but arises a lot within the double copy context. So today what I'm going to tell you about is a double copy relationship for special theories that live in 3 dimensions, which are the topologically massive theories, which are defined in the following way. So topologically massive Yang-Mills is just your standard Yang-Mills term plus the addition of a Chern-Simons term. And topologically massive gravity, again, Einstein-Hilbert plus your Chern-Simons. Now, these theories are interesting because they bake parity. They only have 1 degree of freedom that depends just on the sign of the mass here. It's going to be like a plus or minus 1 helicity state or a plus or minus 2 helicity state. And we have shown that it satisfies the double copy relationship that I mentioned before, that is usually for Yang-Mills and gravity in d equals 4 or larger. So you want in d equals 3, these would be the theories that you could be looking at. So we have this double copy relation, and we have shown that it holds for amplitudes at 5 points at 3 level, which is already very hard because this is the first non-trivial test when you have massive theories and you have a double copy relationship. Also at all loop for an Icona limit, thanks to the resummations that you can do. And furthermore, there's a classical version of this double copy that you can do in coordinate space that I will introduce in a second. And there's what we think now of a more fundamental version of this that you can derive these classical versions from, which is from twistor space, which is what I'll start mentioning later in the talk. So let me go to the coordinate space version. So the idea of this double copy is to relate the curvature tensors of the gravitational side to the curvature tensors of your gauge theory. But instead of doing it with tensors, there's a better way of doing this that simplifies our calculations, which is spinors. So for those familiar with amplitudes and spinor helicity amplitudes, this is basically that idea. And for those that don't know, the idea is that you're just going to use the fact that the Lorentz group in 3D is SO2, 1, and is doubly covered by SL2R, which is simply the fact that you can grab any vector that you have and dot it into these matrices that are SL2R matrices, and now you get something that it has two spinor indices. So you could translate everything you had in tensors to things that have now spinors. So we're going to do this for the curvature tensors in these topologically massive gravity theories, and the one that we want to look at in 3D is the conformal tensor, which instead of Weil, because it's going to vanish here, is called the Cotton tensor. And it's this one over here. It's just derivatives over your Ricci tensor. And you can construct this spinorial version in the following form. Now, if this one vanishes, your spacetime will be conformally flat. On the gauge theory side, what you want is going to be the spinor that corresponds to the dual of the field strength. So it's constructed in this way. And the proposal is that whenever you have a classical solution of these theories, there is a double copy relationship that writes this Cotton spinor as a square of this dual field strength spinor, quotient by this scalar. So in this case, this scalar plays the role of the propagators that we had before. So in 4 dimensions, it is known that this can give you a relationship for black holes as a sort of square of electric charges. So the question is if we can do this in curved spacetimes. In double copying, curved spacetimes are very difficult, so we're going to use twistor space as a playground to actually find this double copy relationship. But first, let me show you. So this relationship has been proven in flat space for some specific cases. These specific cases are gravitational waves. In those cases, the curvature spinor stays this simple form in terms of one basic spinor. And when you assume this, if you assume that on this side you have some solution of your topological gauge theory and a solution for a scalar field that satisfies this equation on a curved spacetime, which corresponds to a conformal coupling in 4D, but it's not a conformal coupling in 3D, then by default, this side will be a solution to the equations of motion of topologically massive gravity. So these here are the equations of motion of topologically massive theories that look very simple when you write them in terms of spinors. They look a bit more complicated in terms of tensors, but again, that's why we do spinors, because it simplifies things a lot. So what I've explained so far is that we can have a double copy in momentum space for the scattering amplitudes. And I didn't show you, but in some cases you can do an inverse Fourier transform, and this will show you how you have also this double copy in coordinate space for these classical solutions. But there's another more fundamental space that allows you to do this double copy relationship, and this is the so-called twistor space. So you can start from momentum space and scattering amplitudes and do what is called a half inverse Fourier transform that was introduced by Witten, and you will land in this twistor space that basically is a projective space whose geometry is going to teach you something about your spacetime. And it's also good because from here there's something called a Penrose transform that I'll show you in a second that allows you to transform data from this twistor space to now find classical solutions. So all of this has been done for flat space, and again the question is how do we know what happens in curved spacetime? Do these double copy relationships still hold? And it's a very difficult question. So we're going to use the toy model of these topologically massive theories in ADS3 to answer this question. So now comes the second part, which is introducing the twistor space of ADS3. So this you can think of it as just the space of geodesics in ADS3. So basically, this will be the equation for a geodesic. Now I'm working in the embedding space of ADS3. So this will be a point in the bulk. And now it can be written in terms of 2 points in the boundary that correspond to where the geodesic ends, starts and ends. And these points in the boundary can be given in terms of a single spinor, calling here mu and lambda. And there's going to be a parameter t that just takes you across the geodesic. Basically, you can take these points in the boundary by a single spinor instead of something like here with 2 indices, because in embedding space, these will have x squared equal to 0, which means that you can split the matrix into spinors. So this allows us to now see what the space of geodesics looks like in this notation. And if you want to vary the points in the boundary to different points in the boundary, then you will do transformations that look like rescaling these spinors in this following way by different non-zero numbers. So these are basically isometries of your geodesics. So now we have that this space of geodesics in ADS3 are labeled by lambda and mu. And this corresponds to the Mini-Twistor space. So lambda and mu are in fact just a Riemann sphere, or they're a CP1 because they have to be equivalent under this scaling. So they're not a C2, but a CP1. So this is your complex projective space that we're going to be using to describe the theories. Now, the important thing here to know about classical solutions is that there's this thing called the Penrose transform that gives you a one-to-one correspondence between functions in twistor space, so these ones, and classical solutions. So I can grab a function in twistor space, and this has to have a given scaling according to these rescalings of this lambda and mu that give you, remember, the points in the boundaries. And just take it for granted, these are going to be the scalings. And a function that scales like that can be integrated over a contour in the Riemann sphere that looks like this. So it has the correct scaling so that the overall integral would not rescale with the lambdas. And to get the solution, all you care is about the analytic properties of this f. And you can check that these constructions that you have here will give you solutions to these equations of motion, which hopefully you remember are the ones of the topologically massive theories. So twistor space and the Penrose transform by default are going to give you solutions of these topologically massive theories in this way, and also of the scalar field with the same coupling, now setting the ADS length to 1. So now what's the double copy proposal? In flat space, we had a simple version of it, which just says, well, these functions, the square of them divided by the scalar will give you the gravitational one. So 2 spin 1 divided by spin 0 gives you spin 2. You take the masses to be the same. In curved space, it's going to be a bit different because now you want to keep propagators unchanged throughout the double copy, like in the amplitude case, but that in curved space means bulk to boundary propagators unchanged. So now what you want to keep unchanged is the conformal dimension plus the spin. So the prescription, instead of keeping the masses the same, is going to change what the masses are throughout the double copy. And this will be the relation between the conformal dimension and the topological masses. So the prescription now changes this conformal dimension in this following way for the gauge theories and for the gravitational theory in terms of the conformal dimension of your scalar. So now let's finally reach the double copy for the black holes. So these warp black holes can be thought of in terms of this metric. Instead of having the full ADS3 isometries, which are SL2R cross SL2R, we're going to have this warped ADS3 that breaks the SL2R down to the U1. And now we have a squashing parameter in one of these directions, which is this one. So if this one is 1, you go back to ADS3, and the masses correspond to plus or minus 3, again, in units of the ADS length. And it has a Killing vector that corresponds to this one. And like you do with BTC, if you do a quotient with a discrete set of isometries, you can get warped black holes. An important property for us is that it has this Kershel form, and so it can be thought of as perturbations around this metric that has now a mass equal to plus or minus 3 of the ADS length of this base metric, which doesn't have to be the ADS length of the full metric. So since we can think about it as perturbations around this ADS3 length, we can actually find it as solutions of these topologically massive equations that I was writing before, like this, with this being the ADS3 base metric. And the twistor space correspondence of this solution, it will look a representative that looks like this in terms of spin of helicity variables, not very important what they are, but and they're related to the squashing parameter and the ADS2 length of this one over here. And the coordinate space version also has a simple interpretation. So you can construct it as a double copy of a gauge theory, and this is the equivalent in the gauge theory. So your gauge theory will have in Mini-Twistor space representative that looks like this, coordinate space something very similar, and it corresponds now to a field strength that is in the same direction as the Killing vector of your warp ADS. So it's just basically an electric field in the direction of the squashing. And you have a field strength that's also going to have a Lie derivative that's 0 with respect to the Killing vector of ADS. So physical properties that you will expect of the gauge theory that will give rise to a double copy of these warped black holes. And in fact, in ADS3, it is known that if you know what is your Killing vector, you can reproduce your spacetime entirely out of this. So one thing you can do is just start for your gauge theory solution, say the dual of the field strength is going to give me my Killing vector, and then you can reproduce your gravitational solution. So we checked, and indeed, this gives rise to that double copy in Mini-Twistor space and in coordinate space. So we have now a new version of a double copy in ADS3. And just to conclude, what I've shown you is that there is an idea of how to do the double copy in different spacetimes. While in flat space, we know perfectly well how to do it in momentum space, then we know how to go to coordinate space and to twistor space. In curve space, it's a bit more complicated. Doing things in momentum space, it's not very clear how the double copy would work. So now the proposal is, well, let's start from the Mini-Twistor space and now go to the other directions. And the open question is how to do it in momentum space. Thank you.
Okay, let's see. Questions? Another up there. David, please.
I'm confused about the version for the double copy that you want to formulate in ADS3 because there are no graviton propagating degrees of freedom in 3D Einstein gravity. So can you comment about this? And I have another question, general question.
Yeah, so that's why instead of looking just at Jack Mills and gravity, I do these topologically massive theories. So everything I said is for the topologically massive theories that have one massive degree of freedom. So it would be like a +2 helicity mode propagating in the bulk.
Just to make clear, there are no graviton scattering amplitudes in ADS3.
When you have massive gravitons, you do. So because they're massive, that's the...
Okay. And another question is that in 2022, Fernando Alday in a conference said that the double copy idea doesn't work in ADS. Can you comment about this?
Yes, so that's exactly the problem about momentum space. So when people try to do double copies, they try to do it usually in momentum space, and it breaks down at 4 points. So that's why the proposal is let's not start from momentum space, let's start from twistor space, and let's see if we can understand it from there.
Any other questions?
How sensitive was your final result to the boundary conditions you're imposing on the field? Was it?
It is sensitive because basically.
Even in the slide when you had your bulk to boundary propagators and so on, for example?
Yes, it is very sensitive. It depends, depending on what boundary conditions you pick, you're going to get a different representative here in twistor space, and it might not satisfy the double copy. So we haven't checked different boundary conditions, so it would matter. And it's something that we're trying to check in more detail.
Thank you.
I have a couple. Or is there more questions from the audience? No? Okay. So let me just see if I understood the double copy in this case. So the Yang-Mills theory, is it living on ADS?
Yes, on ADS.
And then so it's a Yang-Mills with the Chern-Simons term on ADS, and that's equivalent, or the proposal that that's equivalent to TMG.
Yes.
With a negative cosmological constant.
Exactly.
Okay. Okay, that's a little bit different than usual. But the question I had, so you focused on the warped black holes. So my first question is, what happens to just the BT set? Because BT set is also a solution to TMG.
Yeah.
It's an easy one.
Yeah.
So do you also have a double copy for that, or?
No, because the proposal is that the things that we're double copying is the cotton tensor.
And the cotton tensor is trivial.
And the cotton tensor is trivial for BTC.
I see.
Yeah. Although, and I don't know if it will work, there could be a version of this that instead of doing a double copy for the cotton tensor, you could do a double copy that leads to the traceless Ricci. Oh, but it's going to be the same in topologically massive gravity, so it's not.
Okay, okay. And then the other question I had is that TMG is known to be unstable.
Yeah.
So what is the version of that in your Yang-Mills theory? Do you have a diagnostic of that? Is it?
So there's a thing with the double copy. Some physical properties don't have to be translated into theories. So it can depend on the parameters that you pick, and it doesn't have to be the case that both are unstable.
I see. Okay. No more questions? Okay, let's thank Mariana again. And